So, hi everyone. Myself, I'm Dr. Naresh Kumar Pendiala, working as a postdoctoral researcher in UHE in Spain. So, my current research is we are focused on fabricating devices, semiconductor devices using perovskite, halide perovskite materials. As you know, halide perovskite materials are they quite new, metal organic inorganic hybrid structure they are, and they are they give some flexibility in device making. Like they are solution processable. They are compared to existing silicon. They are very cheap material, economically viable, and the fabrication process is simple. We need not to use lot of heat or energy for making them, and they are inexpensive. So they also started to show very good properties like solar cells. If you focus on solar cells, they started to give very high efficiencies, reaching 25 percentage power conversion efficiency and more. And they have more feasibility in using semi-transparent solar cells, so such that in the future we are going to have solar cells replacing our glass in the window of our home. If you have your window, you can replace that window with a slightly transparent, I mean semi-transparent glass, so that you can able to produce the electricity simultaneously. So like wherever the glass is there, you can able to replace. So they are semi-transparent. Also in the future we are going to have flexible solar cells using these materials. So we are looking for these kind of materials with high improved properties, such that the challenges currently what they are facing, they are presently the highest efficiency they are reported for lab processing solar cells, like a very small area, and they are like only spin coated most of the times. They are fabricated inside a controlled environment such as nitrogen, inside the glow box. So what is the story? So I'm going to promote my review article. Recently we published that review article where we explained the importance of these halide perovskite materials in fabricating these solar cells, especially particularly while they are going from lab scale to industry scale, such as open air conditions, and changing the formulations to make them stable towards air, moisture and moistured air, room temperature, and simplified fabricational conditions, and large scale scalable applications. When they are moving from small scale laboratory scale to expandable larger scale open air fabricated printing methods such as inkjet, blade, and several other methods, I am going to explain that those what they discussed in the review article. I'm going to explain you that. Okay, if you see my review article, so I'm going to share that article here. If you see that, so this is our manuscript. Is it got accepted in sustainable energy and fuels. Is the review article is published in last month, I mean in January 2025. So this is quite new, and we gathered latest information about printing perovskite solar cells, and we collected lot of information here. For example, if you see, these are the review article. It is the title is like evolving solar cell manufacturing, the promising outlook of open air perovskite printing. The major challenge here, the perovskite stability. If you fabricate the perovskite solar cell inside the glow box, they are quite stable. But what about the stability if you fabricate outside, or if you leave the fabricated solar cell outside? What is the stability? You can encapsulate, still there will be a leakage. So how will you overcome these problems? So the major thing, you should be able to fabricate the solar cell in shell itself open air. making stable towards open air conditions. That's a major challenge for these kind of solar cells. So the major condition we explained, the challenge is open air perovskite printing. So we gathered all the information who they are working on these kind of open air perovskite printing techniques, and what the improvements till today, what the improvements they did, and what is the existing literature, how much literature is there. We can see all in single place. This is the article, that is it is given in it is accepted after peer review acceptance, that is sustainable energy and fuels. If you see, this is submitted on 1st January 2025, and it is accepted after 1.5 month, like 17 February 2025. So if you see in the abstract, we have clearly explained lab scale. When you use nitrogen closed chamber, it is a spin coating method. You will able to fabricate small scale area devices. They can produce high efficiency. But what about large scale open air conditions? And the background color we given green, which means green you towards ambient conditions, non toxic solvents, like we are making towards this. So here I explained H2O, the molecules means inside moisture, and O2, oxygen conditions. So blade coating and the spray coating, inkjet printing, mesh assisted, and R2R slot die method. These 5 techniques mostly I considered, and I collected the information with the help of Ankita and Illam Naidu Ponada. They are my colleagues from when I am doing my PhD. I know them from Indian Institute of Technology. And Antonio Guerrero is my current postdoc supervisor. He is very experienced scientist in perovskite materials, using perovskite materials. He is well expert in memristors and organic organic OLEDs. I mean OLEDs, and he's also expert in photovoltaic applications and solid state electrochemical devices. He is very expert in that. And Leo Edgar is the most known person for halide perovskite solar cells, because he is the one who invented the whole transport material free halide perovskite solar cells from his from EPFL. He worked with Michael Gradgel. So these are our team. We started to investigate on these materials and these conditions. As I said, open air conditioning methodologies, the current strategy, and current existing strategy, and what are the improvements they did recently for making them towards open air condition printable perovskite solar cells with whatever the efficiency. The introduction I explained about what exactly these materials, what the importance for these materials, how they are like, and how they came into solar cells, etc. And what exactly the structure can be NIP, which means N is N-type material, and P is the P-type material. I means is the semiconductor. So when you push the light, when you flash the light, the semiconductor here, perovskite, will generate electron and hole. So these electrons and holes will be scavenged by whole means HTL means whole transport layer. So this will be scavenged by whole transport layer. The ETL, electron transport measure, they are very conductive for electrons, not for holes. So the electron will be taken by ETL. So this is how the charges will be separated and taken into the open circuit, I mean the external circuit, so that the electricity can be produced. So this is like, bottom electrode, top electrode. Why this difference will come? So top electrode is the HTL, which means you can give by solution method. They with that the efficiency will be different. So if you put HTL on the bottom, the ETL, you are restricted for only few materials. If ETL is bottom, you can put some metal oxides. You can heat them at a high degree centigrade, 450, like that. So they are more known. But after that, this HTL you have to give solution, because after putting perovskite, the next layer whichever you are giving, you should know that the solvent should not harm the perovskite, the temperature should not harm the perovskite. So the whatever the layer you are giving up after perovskite, based on that the type of solar cell structure is existing. Like NIP is the most regular and PAN is different. In the I explained why this one, and then mesoscopic, this is most common. Okay, these three structures mostly we can find in the literature. And we also explained, as I explained, when you give the light, how electron and hole will be scavenged by these materials, and what are the challenges in getting these electrons to the external circuit. So I explained in the first figure. Later I explained the what exactly the challenges in extracting in charge, charge recombination. So the traps, the defects, and the thickness, how it affects, and the pinholes and cracks, and the charge traps, and then interface. So these challenges, how they are influencing the resistance, series resistance or shunt resistance, or all the resistances for electron, that I explained in detail. And charge transfer resistance at the interfaces. And moreover, when you put voltage, when you apply voltage, means whenever you measure solar cell efficiency, you have to apply a fast voltage. I mean, you are going to measure the state of the device, which state it is. So when you apply the voltage, the ions in perovskite, they are flexible materials, the ions start to migrate, halides mostly and lead. So these ions will form double layer or some chemical reactions responsible for or ionic penetration towards ETL or HTL. So these are the problems. And what exactly you have to have, what conditions to improve the efficiency. This is what I explained in the figure 2. So, and then what exactly the solution processability, because when you put all precursors like methyl ammonium iodide, lead iodide, uh, something like that, you put everything, but at the end you are going to get methyl ammonium lead iodide AbX3. So this is solid state, this is liquid phase. So how can you, what exactly it is happening, the crystallization process, how this is going to happen in solution. When you put all these three, they are separated. When in the solution, they are like they are attracted by hydrogen bonding or some polar interaction, dipolar interaction. But when they are going to solidify, the how this anti-solvent is affecting or air knife or vacuum methods. Here I did not indicated the vacuum, but vacuum also is one of the key parameter in the coming literature. So air knife, how it works, anti-solvent and heat treatments, they work in order to make the solar cell solid in coming into solid state. So these are the things I explained. ఎందుకు వచ్చాం వాసు మధ్యలో, నేను వీడియో రికార్డ్ ఇస్తాను. అవునా? మన ముందే నేను పాలు తీసుకురమ్మన్నా అని తెచ్చిన. అవునా? ముందే ఇక్కడ పెట్టినా అవసరం లేదా, ఆడ పెట్టినా. ఓ, ఇది రికార్డ్ అవుతుంది. So sorry for the break and interruption. I'm going, till now I explained. So I'm going to share another window again. So now I'm this is what I explained until device, how the device, what is the structure of the device, how this is charge generated, how when you give the light on onto the device, and what are the problems when grain boundaries, dangling bonds, thickness, pinholes, and what are the things will happen, I explained here. And solution processability, and when this is in precursor solution, when it is going to solid thin film, how it changes, I explained all this. And in the current method, in the session 3, I'm going to explain about large scale deposition methods. Here I explained the beautiful scheme explained by Ankita. She's my colleague. She explained about the fabrication conditions. She gathered this information from the literature and explained how this blade coating works. When you move this, what is the solution when you are putting. and the screen, and this is R to R, roll to roll, slot die coating, and inkjet printing, and spray coating. This is the beautiful scheme given by Ankita. And then the literature, all this literature, if you see, this is a massive literature. It is hard for you to go and check individually for you. So we collected all the information, what exactly the what are the efficiency parameters. This is too much for me to explain in a very short time, but I'm trying to make you here the device fabrication. Okay, what is the formulation, what is the device structure, and then by which method, printing, inkjet printing method, or blade coating, etc., and all the layers printed or any particular layer printed, like, and the efficiency parameter, what is the efficiency, and other voltage, VOC, open circuit voltage condition, fill factor, and current density, the parameter, solar cell efficiency parameter. After that, what is the important thing they from this paper, like focused on electron transport layer, ink engineering, what is exactly what they tried from this paper, like novelty, solar solvent engineering, digital control, etc. I explained here. I mean here, and what are the conditions, and whether they used anti-solvent or not, and the reference. So this is massive information with full of literature. Is I took the help of Prudvi Naidu, is one of our colleague. He explained, he collected all the literature and helped a lot in making this table. And what exactly in later, I tried to explain one after one. Initially, I took blade coating approach, and what exactly this blade coating approach, and who invented the most interesting thing, like air knife, where it is helpful, and what exactly the difference, and how much efficiency they got, etc. I explained. Likewise, every method I explained with full of literature and other stuff. So please go through this paper if you are interested and find the interesting, and yeah, this is one of our paper we cited. If you see here, the in this paper, what we did, this is like printed solar cell. So this is our work from when I'm doing my postdoc with Leo Jedgar. He is one of the co-author here. When we are in a project like producing semi-transparent solar cells using inkjet method in open air conditions, this is our device. So we took additional advantage of flexibility, PE and substrate. Here we put some polymer pillars. I mean, initially we print using inkjet printer. We put some monomer solution, and then we polymerize using UV irradiation. Then the pillars will form. The pillars will grow. Over these pillars, we deposit perovskite solution by inkjet printing. This is everything is at room temperature in open air condition. Then we modify the different surfactant formulations so that we avoid the crystallization from very random and with lot of pinholes. We avoided this. If you have random perovskite crystallization or with pinholes, the possibility for device shorting is very high. That means device is not going to work. So we modify the formulation, putting some surfactants, and which is compatible for printing conditions as well. And we got a very beautiful perovskite morphology. And then if you see, the polymer pillar is a transparent one, here, very regular. And we can also tune the size of the polymer pillar so that we can able to tune the semi transparency of the old device. Like this is semi transparent, this is transparent portion. This portion can be increased and changed the dimensions and everything, so that the overall semi transparency of the device may vary. If you see, it's a flexible and very semi transparent cell, you can see the quantum behind the text. And if you see the same area with and without polymer pillar, you can able to clearly see the semi transparency, how it is increasing. The transparency of the device is increasing in this portion after putting some pillars. So this is the work I also put here. So a lot of literature we you can find lot of things here. So so with this I'm going to conclude. So if you find some interesting things, you can go through this paper and find most interesting things. Okay, thanks for watching, and have a good day.